And one benefit of this particular problem or section, because here we consider a single slit, is that we have equipment for you to do a lab with light going through a single slit. That's one benefit. We can do a lab on it. But we consider different geometries over here. The first one is that we have a single slit, not the double slit. In the double slit, it's like you have two doors separated by a distance d between them. But the width of the door, it's the width of the slit. The width of the slit at the top is the same as the width of the slit in the middle, is the same as the width of the slit at the bottom. So it just, but what matters for the double slit interference is all you need is the distance from the middle of one slit to the middle of the other slit. Here in this chapter, we consider just a single slit, like just one door. And the waves go through the door, and that's it, right? You don't have two of them. Later on in this same section or chapter, and you see the diffraction pattern is not so symmetric like in the case of the double slit. But then what I would like to consider next is what happens if you have a circular aperture. What happens if you have a circular aperture? In other words, the slit is, if you look at the aperture, the slit is like this. So the light goes through this circular aperture. But notice that the width of it here is different from the width of it here, is different from the width of it there, is different from the width. So this thing has a varying width, and no width at the top and no width at the bottom. So this is like a single slit with a variable width for the slit. And you might say, well, who cares about that? Well, the interesting thing about it is that we have two circular apertures, right? Light enters our eyes, and it's a circular aperture, right? The pupil, it's circular. So what changes if you consider the fact that the width of this is changing throughout? How does this compare to if you just had a single slit where the width is always the same? So what is the adjustment that you have to make? And I like to say something about that. And then I think there are two more cases, I think. And then there is something called the diffraction grating. Diffraction grating. There's something called the diffraction grating. And in a diffraction grating, you have not one slit or circular aperture or two slits, but you have thousands of slits. And we have gratings in the lab with, I think it's like, I think it's 600 slits per millimeter. Because I don't think it's per centimeter, it's per millimeter. And that's a lot of tiny slits, right? So in a centimeter is like 6,000. In 1 centimeter, 6,000 of them. And then what happens in that case, you'll see is that the light goes through them, right? And then there's a screen over here. And then, see, in the case of the single slit, let me show you the diffraction pattern of the single slit. It's like this. There's a broad, bright band in the middle, but then you get dark, bright, dark, bright, dark, bright, and so on. So there's a big bright spot in the middle, but then dark, bright, and so on. With the diffraction grating, with thousands of slits in there, you get like a bright spot in the middle, and then dark, and then boom, bright again. And then dark, and then boom, bright again. And then you don't see any more. So you might just see like, a bright, and then in the center, and then maybe one or two bright ones, and then that's it. And they're really spread out. From the bright to the bright, they're really spread out. And the reason why I want to talk about that particular problem is because there is an instrument that we have in the lab that we will use. It's called the a spectrometer, like this, where you put the grating over here, and you have light coming in from a hydrogen gas that's been excited by an electric current that's passed through the gas. So you have this tube with hydrogen in there, hydrogen gas, and then you just connect it to a power supply, turn it on, there's a big current, just a flow of electrons going through the gas. The electrons, as they go through the gas, boom, 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 they collide with the hydrogen atoms. And the hydrogen atoms get excited to higher energy levels, and if they don't get hit soon afterwards, they go back to their ground state and they emit light. And the light that's emitted, well, it emits light in the infrared and as well. I'm sorry, in the ultraviolet as well. But we're only going to see the ones that we humans can see in the visible, from about 400 to 700. And so we want to pass that light right through this diffraction grating, and then use this instrument. If we look at the right angle, we're going to record the angle at which we see the light from the excited hydrogen atoms. And this angle, there's a one-to-one correspondence between the distance between the slits, this angle, and the wavelength of the light. And then we can use this to measure the wavelength of the light emitted from excited hydrogen atoms. So it's part of an instrument that we'll use later on in the lab. Right? So that's why I want to. So, I kind of want to skip it, this chapter 36, but at the same time, we have circular apertures in our eyes, and then you talk about the Hubble Space Telescope. It's got a mirror that's like 2 meters in diameter and circular, right? So then you talk about the resolution of it. How far can you see? And so there are questions that relate to this topic, and I might as well just talk about it. After that is relativity. That's special theory of relativity. But then I would like to cover at least a couple of these chapters over here. It seems like we're running out of time pretty soon. And relativity is pretty long. It's a really long chapter. But of course, we don't have experiments for that topic. But we'll try to get as much done as we can. I don't want to skip relativity. And then we'll go back to photons. There's a problem where that was solved, where you consider a photon as a single particle coming in and collides with an electron at rest. And then you apply the equations of relativity that Albert Einstein came up with for linear momentum, conservation of energy, conservation of linear momentum, using the equations that Albert Einstein came up with for the correct equations for energy and momentum and kinetic energy and so on. And then you work through the problem. It's just in physics 185, you consider a block colliding with another block. And maybe they went in different directions, right? Then you use conservation of linear momentum along the x-axis, conservation of linear momentum along the y-axis. If the collision was elastic, then you can use conservation of kinetic energy, and you can figure out which way they go and how fast the objects go. Here we want to do kind of the same thing, but we want to consider a photon as a particle and an electron as a particle. And then they collide and they go off in different directions. And we want to use conservation of the x component of the total linear momentum of the system, but using the relativistic expression for linear momentum. And conservation of the y component of total linear momentum, but using the relativistic expression, the one that Einstein wrote, right, for linear momentum. And conservation of energy, E equals mc squared, that one, we're going to use that one. And there's going to be quite a bit of algebra, okay? And that problem, I plan to give it to you as a take-home. So, solve it. This is the answer. So you just do the algebra. It's just algebra. It's not like, heavy-duty math. Just algebra, then you get to the answer. So I kind of want you to work on that. So, but it's a relatively long problem. If you were to do it, you have to manipulate some equations here and there. The textbook actually kind of tells you what to do, but then it gives you the answer. So I want you to work on that since you did problems with collisions of objects colliding in the equivalent of physics 185, so then I'm gonna ask you to do that one. It'll be fun, right? And it was a very important calculation, and then the experiment was done by Compton. It's called the Compton effect. So then the experiment was actually conducted by Compton in 1923, I want to say. But anyway, you'll do the calculation, and then the experiment just showed that it really matched what was predicted from using Einstein's theory of relativity, and then that's when people began to take Einstein more seriously, because he wrote the theory of relativity, the special theory of relativity, which we are going to learn about, in 1905. But then, he was, there were a lot of people that were not happy with it, and he was like arguing. But then there was experimental verification in 1919. There was a solar eclipse, and then, wow, And then in 1921, they gave him the Nobel Prize. But not for relativity, they gave it to him for something else. And then in 1923, I think it was, the Compton effect was another experiment that then said, Einstein's got to be right then. But they still never gave him a Nobel Prize for his theory of relativity. So that's the plan. I'll see you on, do you want a quiz on Thursday?